Okay, I'm recording this session and I will upload the recorded video to the channel. Okay. Yeah, please go ahead and so I hope Week-9 content is fine. It's not that much hard, but of course there are a variety of different types of topics covered across Week-9. Starting from, I mean, it's all about word representation, but a number of techniques. So the thing is that today it is kind of obsolete. I mean, in the sense, in natural language processing, for so small tasks, we still keep using these representation, but for some high-level tasks like question answering and text generation, so now we are almost kind of we are not using this, you know, text representation techniques. Okay.
So it's all moved to transformers now, sir.
Yeah, transformers. The thing is that even before transformers, people started using something called as embeddings, which they train those embeddings during the training itself. Instead of getting the representation for each word, which are fixed in some sense, people started training these representations in the training phase or something called as pre-training phase. So what we have learned is a static embedding for a word, but there is a concept called contextual embedding for each words. So that is what being used right now, even for the past 5 years.
Oh,
It is like the representation for the word bank is fixed in all the techniques, right? Whether it is word to wake or SIBO or whatever, the representation for a given word bank is fixed independent of the context it appears, right? The bank
right.
may point to an financial institution or it may refers to that river of the sites of the river, right? So typically all the words have multiple meanings based on the context. So it is always good to get a different representation for you know for a same word in a different context. So that's the thing right now. Yeah. So any question in Week-9
The
in general?
I had question my personal difficulty because I think even in MLF, SVD is one part I was very not comfortable with for some reason, right?
Uh,
So I didn't realize SVD is going to be useful. I'll read it upon it, but I know often what happens is that between the NPTEL courses, between our courses, even between our courses, right, between the instructors and the professor, sometimes there is a notation difference. So
yes.
so what was he? Because it seemed that in the NPTEL course they had covered SVD very clearly, and then he was referring to those things. And
Hmm.
for us, it was kind of new. But I want to get an idea about the notation that they have used. Sigma
Notation in the sense,
for
so
the very
kind of variables involved in
yeah
the decomposition. You mean, right?
yeah. He's just saying sigma delta, and these are the two matrices. And I was just trying to ensure that that's the same notation that we have used.
Oh, that's same, right? So, okay. So if I have a matrix A, now here we have a matrix X, right? So we decompose this into three, or we factorize this into three matrices. So I don't know in what notations people use it in MLF and MLT. I do remember that, but I'm not sure whether this is U sigma V transpose. Is this correct? I mean, this
Yeah,
is
that's correct. I mean, that's what was used in MLF.
yeah, because in fact, during the first offering of MLF, right? So I handled SVD. So
Yeah, you had a tutorial, a couple of tutorials actually.
yeah. So I think we are using the same notation here. Am I right? So U stands for say for example, if my X is of size M by N, okay, it could be whatever. M could be a representation for a word or whatever. It's just size of M by N. Then we decompose this into say for example, U will be of size m by k, and sigma will be of size, it's a square matrix, k by k, and then V transpose will be of size k by n. And sigma is a diagonal, as usual, it's a diagonal matrix. And U and V are, of course, if X is a symmetric matrix, then U and V is going to be, orthogonal. Typically, we use V inverse, but before computing SVD, we make the matrix symmetric, so it's U and V transpose, and all the vectors are orthogonal. So the same properties. What is your specific query, Srinivasan, so that I can focus on that?
No, I want to ensure that we are using the same part so that I will go read up again on SVD, right? And then that way, because without that, the lecture was not making sense without knowing SVD. Yeah, and I couldn't
Yeah,
remember my
and
SVD. Yeah.
maybe one thing, if I remember correctly, that was not covered in machine learning foundation course in the lectures is that how this approximation emerges from these three matrices, right? So we use sigma 1 and then U V transpose the rank K approximation, right?
Yeah, that
But
is
I
definitely that is new. Yeah, maybe you can just describe that part.
uh, okay. So the thing is that
This was your
when
sorry, no, no, sorry to interrupt. I think this was this one tutorial where you had Abdul Kalamji's photo and you kind of explained this linear information thing. That's my vague remembrance.
yeah,
I
that is
can't
right.
remember.
So I, in fact, from the application point of view, I took that where we
Right.
approximate an image using different rank of approximations. So that's where
Yeah.
this exactly, I mean, you can match with that one. So the thing is, when you look at U, we have all these U1 and U2 all the way up to, okay, just say I have some m rows, right? And then this is going to be a diagonal matrix. So sigma 1, sigma 2, of course. Typically, we arrange these sigmas in a sorted order where sigma 1 is greater than sigma 2, like that. So, which is somehow you can think of it as capturing the variance, sigma k. And then similarly, we have a matrix V, right? So, which is V1, let's say V2, all n rows, right? Sorry, there must be k rows. Okay, so what we are trying to do is that I can think of like when we write a number 10, right? So we can approximate this number. By the way, for the sake of argument, I need to only use number 3. Okay, then I can approximate this as 3 plus 3 plus 3, right? Of course, I can't add 1 because I supposed to use only 3 and I am not supposed to use any other coefficients. So it's like I'm decomposing number 10 in using some, of course, this is a one of the prime. Is that a prime number? 1, 2, 3. I hope so, right? So like that, I can decompose this entire matrix X, or I can approximate this entire matrix S using different ranks. So what is that? What do we mean by that is that, let's say each row of this matrix U, what will be the size? So this is of size m by k. So each row is going to be of size 1 by k, right? And I can take this sigma 1 and then I can multiply. Of course, either you can multiply it here or here. This is just going to be a scalar, okay? Or you can come in the reverse order as well. So what I want is my the initial matrix size is m by n. So can I construct a matrix of size m by n using these elements? Okay, I take one row and then am I going correct? M by k, so yeah.
The
Then
other
this
way
is
around. So I think U is going to be, I think it will be column vectors, right?
yeah, yeah, that's correct. So that is going to be m by 1, right?
Correct. Yeah.
Maybe I can write this. I don't know how to delete that. Okay. So let's write outside. So I take one column and then I scale it by sigma, right? And then I have a vector v which is of size, what is that? K by n. Okay. Then I can take v1 transpose, which is, of course, you can play with this. You just ensure that the dimension matches. So 1 by n. So what we do is that I take one column vector, only one column vector from u, and then one scalar from this sigma, and then one vector from this v, and then I just do this product. Then I will end up with a matrix of size m by n. Okay, so and obviously we know this is an outer product, so the rank of this matrix is going to be 1. So I can keep repeating this. I take the next vector from u and then multiply this with sigma 2 and then take the other vector from v. Then I can generate other matrix of size m by n. So if I add these two matrices together, then the resultant matrix will be again of same size, but now it will be rank 2. So one way to interpret this is that I can say x is approximated with different types of different sizes of matrices, uh, and k represents how close the approximation is. Typically you can relate it
Sure.
to pca as well.
Sure.
In pca also, this is kind of, what is that, it captures almost all the information, right? So the maximum variance, so we can go with this if we want, but if we add few more information, then we can go with k rank approximation. But whatever, it is consistent with whatever that you have learned in mlf or in mlt. I guess in mlt also arun sir talks about using svd for pca. Hopefully he followed the same notation. I guess I haven't taken a look at the contents, but I hope this is sort of standard notations. Okay, so I hope this helps you. So after, if you just dig a little, or if you refer to other sources in internet, I think those things will help you to grasp all these concepts.
Sir, one issue I'm having with this is trying to visualize the relative importance of the features. Um, so what I'm not able to understand fully is that, see, we create this co-occurrence matrix,
Yeah.
which is kind of giving you this word to context relationship.
Mm.
And then you're calculating, you're then doing an SVD to arrive at a similar matrix. And then you can apply rank approximation there. But how does it show the relative importance of, I'm not able to understand the geometrically or even intuitively, how does it relate to SVD? How does it relate to these two, the word and the context?
Yeah, so that's why we call this as latent, by the way, which means we can't, some sort of give some reasoning, right? So how these words are, say for example, even if I remember that correctly, say, because the first word is human, let's say other word is machine. So initially in my corpus, the human never appeared in the context of machine, so I mark it as 0. So I fill the entire matrix up. Then I do svd decomposition, right? Then I reconstruct it, and then all of a sudden it has some value 0.2.
Right.
So which means what really happens is that when we do this svd decomposition, it looks at all the words, and both the words and context, all the possibilities, right? So somehow it connects this human with machine, because it captures, that's what we believe. So behind the scene, svd take a look at the global picture of the entire corpus, and then by doing this ranking approximation, we are able to get these relations. Of course, when you reconstruct fully, we end up with the same matrix, but once we return to this maximum variance and we ignore the minimum variance, even you can think of it as noise. So where the variance is really minimal, right? So by doing so, we can think like this, but it is very difficult. I mean, giving an intuitive explanation with some examples is kind of difficult. We can give
Yeah,
various
yeah.
interpretation viewing from different perspectives, but this is one of the interpretations, right?
So for images, it was a bit
And
more intuitive, right? It seemed a bit more intuitive.
yeah,
No, it's intuitive because we can see that, right? So even if you reconstruct the rank one approximation in image, it looks like kind of nothing, right? It's you see some sort of constant image. Even then, as you keep on adding, if you go move on to higher ranks, then you can see some object emerges. We don't know how all these details are added bit by bit as we keep on increasing the value of k. But since we are able to see that it is being reconstructed by adding minor details as I just keep increasing the rank, we are comfortable with that. But in words, of course, we are arranging things in a different order, and we are in fact break down the order, right? So we read the sentence and we are just measuring the co-occurrences, and then we put things in order, and then we do this decomposition. Then we get stuck. I mean, get stuck in the sense we are not as comfortable as we with images. We, that's good, right? In the sense you keep questioning and until you get satisfied. Otherwise, either you end up doing some innovative research, or at least you get some deeper details.
but behind the scenes, what is really happening? I mean, if you just look purely from a linear algebra point of view, what is it really doing? So it is, I mean, one is that you have your V transpose, which is an orthogonal matrix transpose. So it rotates the image in one image of this particular context in a particular along that axis, right? So it kind of makes it into one axis, right? So I'm just trying to understand what it really does, because if it scales, because all that sigma 1, 2, 3 that you have, they are all
Yeah.
effectively eigen values, probably the square root of eigen values or something, right? That's what the SVD does, if I'm not wrong.
Yeah. Yes. Yes.
So it scales by that much, right? So it scales your eigen vectors by
Mm.
that much, right?
Yeah.
Uh,
Exactly right. See, what we are doing is before computing SVD, what we do, we take X and X transpose. We multiply this matrix, right?
correct, yeah.
So essentially, what I have is I have one row here, which is a word representation for human, and I do transpose this matrix. Then what I have is that I have a column here that might belong to some other word, right? Maybe human starts here. So essentially, I'm doing this inner product. So by doing this matrix multiplication, I take row times column multiplication. So you can think it of you are measuring an inner product or some sort of similarity by doing this, right?
Right,
Now you have some similarity score, how the word gets. So here you are establishing a similarity. It could be 0 or 1.
right.
I mean, in the interval 0 to 1, if you normalize this, then I do this decomposition, right?
Hmm.
That's where I do this sigma and then UV transpose. Of course, as you can see, now we are computing the eigenvalues of, essentially it boils down to, if you take or remove all this interpretation, you just, if you think of this as just some numbers, you know, arranged as rows and columns,
Hmm.
then eventually what this eigenvalue eigenvectors represents, so it is actually pointing in the directions where the data is actually varying much. So if you
Right,
arrange that in an order, right?
right.
I mean, now you can correlate this with all the concepts that you have studied in linear algebra. So we are moving to different coordinate system. Here we are in canonical coordinate system. Then by decomposing this, then I move on to the coordinate system represented by these eigenvectors, right? We just switch from the canonical coordinate to some a different coordinate system which is kind of rotated, and of course these vectors are eigenvectors, right?
Right.
And then you scale it down. Of course, this part is, you can think of this as analytical part, right? You move your data from one domain to another domain, which means from one transform canonical coordinate system to an eigenvalue, a rotated coordinate system, where each eigenvector is kind of, it's exactly fits with this
Right, right.
PCA concept. So and then somehow when we do this I mean there are multiple ways of viewing this, the concept of variance. Statistically it is just variance. uh, we start with maximum variance and then all the way go to a very minimum variance. So from signal processing perspective you can think of it as the presence of noise. Okay, this is full of information, and as you go, I mean if you go to different eigenvectors, sorry, eigenvalues, then you are moving from information to noise. So you have to truncate somewhere to retain only information and remove the noise. So these are all interpretations. Mathematically the process
Right.
remains same, but when it works then
Yeah.
people come up with different interpretation, and then they try to validate this interpretation is quite correct. So they do all sort of things, right?
Explaining it backwards. Like he saw some result and then explain it backwards. Right?
Yeah. That's often, only when things works then people start digging into details and try to come up with different interpretation and then validate. Then someone comes and proves that that's not good, this way is much better. But I think technically they call it as latent, kind of latent semantic analysis or latent Dirichlet analysis. They use all sort of words. But the thing is the space is latent, so we can't interpret it, I mean, exactly. Oftentimes we know we don't need to worry about that too much. Yeah, single, you raised your hand for long.
Oh, so like I was confused with this word context for this part. Like, are these columns in number of rows, are they like equal to each other or they are not? Like first we started with them being symmetric matrices and then we like converted them to non-symmetric matrices. Like I didn't understand how they became non-symmetric matrices.
When you take x and x transpose, it becomes symmetric, right? That's why I mean, if you have already square and symmetric matrix, if my data in itself is square and symmetric, then I can go with eigen decomposition. But when I have non-symmetric or rectangular matrix, then we go with SVD, right? That makes the data, I mean, before doing any decomposition, it makes data symmetric. So you can think of it as computing the covariance, or if you are, if you just think of x as a ram, some sort of a matrix that is sampled from distribution, then you can think x and x transpose as computing the covariance of x and then doing decomposition. So SVD is by default applied on this metric matrix.
Okay, thank you, sir.
Yeah, so there are a lot of concepts in week 9. So I hope they are all manageable. I mean, even you need not to go deeper into each of these concepts, but at least you know what all these concepts are and how they works. And one important thing that is still being applied in, you know, this transformer era is this hierarchical softmax. So try to understand that, because that is really useful if you are going to work with some deep learning applications related to NLP or computer vision. You end up being using this hierarchical softmax. So week 10 is quite difficult, and week 11, if you are able to solve the assignment questions of week 10, then you should. It's just an extension of the same concept in week 11, so you can solve that quickly. So if required, I may extend week 10 deadline, or I can make it same with week 11. But let me see. Let me wait until Wednesday. Okay.
So straight away, I will request if you can extend it. Great, at least till Sunday. I haven't seen the syllabus yet because I'm still kind of catching with week 9. But anyway,
Yeah, well,
look
typically
at
I
it.
do that. I mean, in all these terms, that's what typically happens. Week 10 and week 11 deadline or due date, falls on the same day. Of course, your eligibility to appear for the final exam is calculated based on the assignments you have submitted. I think up to week 9, right? So it's not a big deal to extend week 10. Okay, so if you have any other questions or if you want to discuss any other thing, we can. Otherwise, we can close this. And yeah, few of you are asked asked about the concepts like BERT and then GPT. It is not being covered in deep learning. Of course, we are taking all those topics to upcoming LLM course. So we will cover all of them in great detail in LLM's course. Okay, so
When is that
Oh,
getting
there is an
released?
LLM course. I don't know whether you know that.
yeah, we are making LLM course. So it will be offered in Jan 2024.
That will be a great
So
course.
deep learning is the prerequisite. So whoever completes deep learning can take that LLM. And of course, I think the bonus activity assignment is on due, I think, on Sunday. Please ensure that you submit it on Sunday. That's those are really simple questions, so you can submit it, right?
Are you planning to have more than what you have already given? Or more than 3? Like, will you have more bonus assignments after this?
No, only 3. So I will release the 4th one next week and the 5th one the week after.
Oh, okay, no, 2 more. Okay.
And all of them are going to similar to this assignment 3, where you need not to code anything, but just go through the resources that I point to, then just find out the answers. Okay, so I hope everything is going smoothly in the classroom. Quiz 2 results were quite awesome than quiz 1, but still I observed there are some, only the pass percentage of the entire classroom is just 52. So the majority, I mean, half of the class were unable to crack this quiz 2. I don't know why, even though most of the questions, I won't say most, but at least from the marks perspective, about 60% of the marks, right? The question belongs to 60 points were repeated almost from the previous quizzes, but still there are few who were unable to crack this. So study well. Week 9 and week 10 and week 11 are quite intense. Not week 9, week 10 and week 11 are quite intense, and please study them as well. Okay. Okay, then we can close this.
Okay, so thank you so much.
Just,
Yeah, if you have any question, you can stay.
yeah, I just because I also heard that people found the quiz 2 difficult. So I don't know whether there are any specific questions from quiz 2 that people had concerns about. I think some differing interpretations of that update question we have discussed on discourse. But did you come across any question that was conceptually difficult, or I didn't find any. Of course, I didn't get good marks, but that is different. But I didn't find anything that is conceptually tough.
So you're asking me whether I had something in my mind while I setting up these questions.
No, not that way. I'm saying whether some other discussions, because I do hear the same feedback that quiz 2 people found difficult, and I'm trying to find out what was the difficulty in.
Oh, I don't know what was the difficulty. So one thing that I keep observing, the same pattern repeats. So, right. So meaning that if you compare their GAA with their marks, right? So I mean, their mean GAA. So they have submitted. I mean, all of you have submitted. I think 8 assignments, right? before quiz 2. So if you compute GAA and plot their score, most of the students' GAA matches with almost, even though it is not within their variance, matches with their, I mean, their quiz 2 score is almost correlated with their GAA, which means somehow I'm just once again hypothesizing, right? Or I'm just assuming that whoever solving these assignment questions and also previous year questions on their own are able to at least pass the quiz exams. That's I just once again observing from the data, but of course there might be some rebuttal. So I am solving all the questions, but I'm unable to get the marks. For them, I have no clue. Despite giving the partial marks, they are unable to pass the course.
Yeah, I may be the slight exception that my GA scores are definitely worse than the. Not that the quiz scores are great, but the GA scores are worse than my quiz scores for some reason. End up making some silly mistakes in GA.
Yeah, that is reasonable. You make mistakes in GAA, so by doing that, you learn it. You learn the important steps or important thing that you need to focus. Then you apply it in the exam. That is good. I mean that makes sense. If someone gets low GAA, but their quiz score is higher than GAA, that absolutely makes sense. But if someone gets high GAA, right, near 100, but quiz score is less than 40, then that doesn't make sense. Why is that the case? The some quite unpleasant, I won't say unpleasant, but shocking observation is that